Thank you for joining us for this webinar on how to select the ideal linear bearing for your medical application. This webinar is being hosted by Motion Solutions. For those of you that are in the live presentation, feel free to type your questions using the Zoom platform. The presentation will take close to 45 minutes. There's a lot of great content that we have to go over with you. After, as Wally has gone through his presentation, we'll use whatever time is available to respond to questions, and we'll extend beyond the 45 minutes if there are additional questions, and we'll get to as many of those questions as we can. Motion Solutions provides custom application-specific engineered systems to OEMs and industrial customers in medical, life sciences, semiconductor, robotics, and other industrial automation sectors. We provide a complete selection of services, including electromechanical design, prototype, and volume manufacturing. My name is Peter Hoffman. I'm the Vice President of Marketing for Motion Solutions, and we're pleased that you could join us for this session. Our presenter for the session is Vice President of Engineering at Motion Solutions, Wally Logan. Wally brings in-depth engineering experience and knowledge in designing from simple to highly complex custom electromechanical subassemblies. We understand that you and your company deeply understand the science involved in your technology. Wally and Motion Solutions deeply understand motion, and today we look forward to discussing selecting the ideal linear bearing for your medical application. And now it's my pleasure to introduce Wally Logan.
Thanks, Peter. Welcome, everybody. Today we're going to be having a general discussion of selecting linear bearings and applying them to medical applications. This is going to be a general discussion, so we're going to be discussing some bearing basics, go over a general process of selection, and then we're going to be talking about some applications that we have done and what we chose as the linear guide or linear bearing for those applications. In medical and life science applications, just to review, many of the applications can be have high performance demands. This might be in running accuracy, it might be in speed, it might just be the fact that some medical equipment can run in laboratories maybe up to 24 hours a day. Also, generally, low maintenance is a requirement. Often, especially for like tabletop equipment, we might have tight constraints on packaging, position error, efficiency. Many times you've got a very small assembly where you've got very small motors moving things back and forth. So you're concerned about the friction. As I mentioned, high duty cycle, and these generally need to run for a long lifetime, many years in the field. And of course, at the lowest possible cost. Some of the problems that we've seen in medical applications that we'll be trying to address here. Improper guide chosen for the orientation. We recently saw a robotic surgery application whereby customer was using a two-row linear, square rail linear guide, and the orientation of the guide was such that it was mounted on wall mounted, and the resulting load on the bearing was a lateral load. And as we'll talk about a little bit here shortly, lateral loads are not necessarily good for a two-row bearing. And it resulted in premature failure of the linear guide. Some other things, improper mounting tolerances. This is probably the #1 issue that we see. Customers not specifying proper mounting tolerances or being able to meet the requirements that the manufacturers select for the linear guide. Some other things, the bearing is too stiff or not stiff enough. You have sloppy motion, not smooth motion. Sometimes if you specify too high of a preload, you might get rough motion from the bearing, or too much friction, which might cause issues with your motor sizing and or tuning. Premature failure, as I mentioned, and often corrosion resistance may be overlooked. Had an application where the customer sent me a picture of their machine that went to over to Asia, and all the rails were completely rusty because the equipment was designed here in the U.S. with relatively low humidity, and that was overlooked. Went over to Asia where there was a lot of humidity, and the rails got all rusty, so that wasn't good. Or overly large or undersized bearings for the particular application. The result, the application may not meet performance, packaging, duty cycle, lifetime, or the budget. So we're going to talk a little bit about some bearing basics. If we got engineers on the line, you probably know a lot of this, but I think it's worthwhile to review. So generally, what you have to choose from are linear guides with balls, linear guides with rollers, or linear guides with plain bearings. Plain being no rolling elements, and so you just have sliding friction. The linear guides with balls are generally, enclosed in the raceway between the linear guide and the bearing block. Generally, they have 2 or more rows. So you typically see 2, 4 rows, and there are some linear guides out there with 6 rows, although that's debatable whether that really gets you anything. And most ball rails are recirculating so that the balls enter and go out of the load zone of the carriage and return down along the block and re-enter the load zone. So basically, as long as your linear guide is, as long as the rail is, the block will continue to stroke. Linear guides, just FYI, so depending on the size, but on some of the larger size rails, they can go up to 5 meters, and they can have joined rails, in which case, so you can have very long travels. I've seen rails with joined rail systems of 20 feet or more. Next would be linear guides with rollers. So a roller has a line contact, and we'll talk a little bit more about that, but what that results in is generally a higher load capacity. These can be had in recirculating and stroke type bearings. And when I say stroke type, what that means is that the stroke is limited generally by the length of the rails and the length of the carriage, and the rollers do not recirculate. And then we've got plain bearings, which are usually a friction type material, a liner put into some type of a housing, and they just literally slide along the rail. You generally cannot preload these types of bearings. They must run with some friction or they would overheat. So you have for medical applications, what we consider a sloppy fit. You're going to have a lot of clearance. Even if you use 2 rails and multiple bearings, you're still going to have, they generally will run with a couple thousandths clearance or a little bit more. And so you're really going to notice that, especially if you have overhung loads. Another thing to keep in mind with plain bearings is life is unpredictable, where with balls and rollers, the life is based on the fatigue properties of the material. In plain bearings, it's not predictable. So there are no really good calculations of life of plain bearings. So, and they also generate particulates. So we tend to stay away from plain bearings for medical applications unless it's a really, really basic application. Now let's talk a little bit about preload. So start on the ball type. So the ball sits between, in the raceway, between the linear guide and the carriage. And so there is no adjustment. So when the linear guide is ground and the carriage is ground, there is a resulting nominal amount of space designed in such that, let's just say it's a 1/8 millimeter ball or a 1/8 inch ball nominal. And so the factory will grind in that, basically they're shooting for that nominal size, but of course they have grinding tolerances. So you have a resulting plus or minus tolerance on the rail, a plus or minus tolerance on the block. And so when you put that nominal ball in there, it may be tight or it may have clearance. And so how does the factory accommodate that? Well, they have gauge balls in the nominal size of every ball size. And in this case, we're talking about 1/8 balls, but in 1 micron increments. So they'll have 1/8 ball plus 1 micron plus 2, all the way up to plus 20 microns or above, and minus 20 microns or above or below. And so by doing that, that's enough tolerance range such that they can take up their grinding tolerances and select the proper ball that results in the right fit of the bearing on the rail. Now, they generally offer normal clearance, which would be a range of anywhere from a couple of microns clearance to a couple of microns of preload. That's what they call normal. And then you go to specific preloads. With the smaller type of rails, the smaller 2-row type of bearings, you're generally only allowed a light preload, which guarantees, say, a micron to maybe 3, 4, 5 microns of preload on the bearing. On the larger rails, there's a heavier preload selection, and you might have 10, 15 microns of preload on the ball. And so when there's preload, the ball is actually compressed, has to compress by that amount to fit between the block and the block and the rail. And so what that does, it eliminates any free clearance and pre-compresses the balls and increases the stiffness. Now let's talk about roller type. The recirculating roller type has the same type of preload available that we just discussed with the ball type, whereby they adjust the preload with the roller size. And then there's the cross roller stroke type bearing. Now this type, the preload is not built in. Though the cross roller type, unless you order it built into a table, you're basically designing it to be built into your system. Each rail is mounted, and as part of the assembly, you will be preloading that cross roller with set screws and doing it manually and setting the preload. And so because you're doing it and the factory's not doing it, there's a lot more chance for problems for not accomplishing the preload correctly, not either the magnitude of the preload or making the preload even along the entire stroke, which can cause big problems. If the preload is uneven, whereby it's heavier on one end and lighter at the other, it can cause the cage, the set of rollers and cage to migrate to the lightly loaded end, and that can cause, and all of a sudden you're hitting the end stop and it causes a problem for your motion. Let's talk about some different types of guides that are available. We'll start with the round rails. So basically you've got a ball bushing on a round shaft, and inside that ball bushing is a ball recirculating. And as you can see on the diagram on the right, a ball on a round shaft results in a very small contact area. And so what that results in is low load capacity, for the size of the bearing. And it also results in not being able to preload a ball bushing. Now, ball bushings are low cost. They are forgiving a misalignment, but they must be used in pairs. Now, we don't use a lot of ball bushings. for the reason that you generally have to use a much larger ball bushing for a particular load application. And in most medical applications, we're concerned about size and packaging. But they do have their place. If you have really loose requirements, you don't have really any space constraints, and you just need to move a load from A to B at the lowest cost, then you can consider the ball round shaft and ball bushing. Now let's talk about the square rails. Let's talk about the ball type. Ball type square rails come in 2-row and 4-row types. For the 2-row, you've got 1 row of recirculating balls on either side of the rail. And the raceway is what we call a Gothic arch. So you can see the diagram on the right. It looks like the top of a Gothic window. And what that does is it allows the bearing to have minimum play with only 2 rows of balls. You can imagine if the raceway was actually full radius, that as you apply a rolling moment back and forth across the bearing, the ball would tend to want to roll up the raceway and roll down the raceway on either side. And what it results in a not very rigid bearing. So with the Gothic arch, you basically take out the middle of that radius groove, and you end up with that Gothic arch shape. The good thing is that it makes the bearing more rigid. The only thing that you have to watch out for with Gothic arch or 2-row bearings is that with a lateral load, you're putting the ball into 4-point contact. And since a ball can't roll around 2 axis of rotation, what they end up doing is finding their own axis, and you end up with a lot of sliding friction. And the result of that is that you can't apply more than a light preload to a 2-row Gothic arch type bearing. For many medical applications, that's fine. We're going to show a number of examples where it works very well. Just keep in mind, you want to avoid lateral loads for 2-row type linear guides. For square rails with 4 rows, you do have a radius groove, because now you've got enough rows of balls such that when they're preloaded, they create contact angles, opposing contact angles, and limit the deflection in a rolling moment. What we're showing here is a 4-row bearing with 45-degree contact angles. This is there are block variants available that have different contact angles, but in general, we'll normally stick with the 45 contact angle, because they can take equal load rating in all directions. It makes calculating the loads on the bearings and the life of the bearing more simple. And you don't have to worry, the bearing can be used in any orientation. There are many block types available. You've got standard and wide versions. You can see on the bottom right, we've got a wide version of the 4-row. And so these are very good for demanding medical applications when you have a heavier load. You can afford to have a little bit larger bearing, and when a little bit heavier preload might be required. There are special versions available for clean room or vacuum, high temperature applications. There is plating available, and there are options for dirty environment. Not so much in medical applications, but in machining type applications. You can get special seals, double seals, scrapers if you've got chips all around the bearing and that type of thing. And then we go to the square rail with rollers. These are always 4 rows of recirculating rollers. Now the rollers, because they have a large contact area, a line contact with the rail, it gives you a higher load capacity for basically the same size rail. Also, that results in higher stiffness of the bearing. And so where you might look at using these is where space is really a premium. You may get away with using a smaller roller style square rail bearing than you would with the ball type. And if that's the case, that's really worth paying a little bit more. And you're going to pay a little bit more for recirculating roller type bearings than you will for recirculating ball types. These do have the various block types available. And one thing to keep in mind though, because the bearing is stiffer, you have tighter mounting tolerance requirements. We'll talk a little bit more about that, but as I said, mounting tolerances and not meeting your mounting tolerance requirements are one of the biggest issues I see with applications. So make sure when you're selecting the bearings, especially a roller type, that you look at those mounting requirements. And before I forget, also for the 2-row miniatures, where you're talking about, you can have a 5mm or lower or smaller rail. They come in 5mm size and also a 3mm size rail, where you've got tiny, tiny balls, much smaller than even a millimeter, the ball diameter is. And when you get to ball diameters that small, it makes the bearing really rigid and not able to accommodate mounting tolerance variations. So that's the other case where you really need to keep an eye on mounting tolerances, is when you're using a 2-row bearing of the miniature size of size 5 or size 3. Now we come to the cross roller non-recirculating type. So you've got roller bearings crossed at 90 degrees so that you can take loads in all directions. So they have a total 90-degree contact angles. They come in size 2 to size 12 rollers. And when I say 2 to 12, that we're referring to roller diameter. But they are limited in stroke. So in the upper right diagram, you can see the cage sticking between the 2 rails. As that cage comes up to the end and hits that screw that's mounted in the end, so that would stop your motion right there. And so as the rail, the top rail goes back and forth on top of the bottom rail, the cage moves back and forth between them and is limited by the stroking of the cage. As I mentioned, these must be preloaded by the end user. You can see in the bottom right diagram the adjustment set screws, and that is what's used to apply the preload to the bearing set. A nice feature to look out for is some manufacturers offer anti-cage creep features. And so if you have a slight unevenness in your preloading, you don't want that cage to migrate to one end of the travel or the other. And then also for vertical applications, just gravity would tend to migrate the cage down. So you can see in the bottom left diagram here, we've got what we call a stud roller. This is from NB, makes this type. And the center roller in the cage has little studs mounted into it, and they basically act like a gear into mating holes in the rail. And so that really acts like a gear, keeps the cage running accurately and centered with both rails so that it will never hit the end of travel. As with other recirculating roller types, cross roller types have tight requirements for mounting tolerances. So make sure that you take a look at that. One other type that I wanted to mention was the curved LM guide. Now this is a type of square rail. This type has 4 recirculating rows of balls, but the rail is ground in a circular arc. What this would be replacing would be typically like a large turntable bearing or thin section bearing. But when those thin section bearings get up to be, pretty large size, they can be difficult and costly, difficult to apply because you generally have to have locking rings on the inner and outer and tight mounting tolerances, and they're very expensive. And so this type of circular guide can be very nice to use. They're available in size 12 to size 65. And again, that's referring to the width of the rail, size 12 millimeters. And many radiuses are available, anywhere from 100 to 3 meter radius. These are generally made up of sections of rails that are joined to create a full circle. You can use some number of sections if you don't have a 360-degree requirement, if you're only moving through a short arc, or you can have a full circle, of course, to have unlimited rotation. You can also add however many blocks are required to support your load, anywhere from as little as 1 to, you could put 10 bearings on there if you have a really heavy load. So that's a nice option to have. One thing that's really important to keep in mind is most bearing types are now available with a ball cage. In the past, this was not available, and the lubrication intervals were really important. If you didn't re-lubricate your linear guide and they ran dry, you would have a catastrophic failure. Now with the cage ball, the cage is a polymer string, and it has a button that fits between each ball. It keeps the ball-to-ball friction, the balls from rubbing, but more importantly, it has a little pocket in there where it's holding some lubricant, some grease, and it greatly extends your lubrication interval. I'm just going to give an example. We had a semiconductor application where we designed a vertical actuator that was supported by linear guides with cage ball, with a heavy moment load. We had about 600 pounds sitting about 10 inches off of the front of the bearings. And we also had a cage ball screw. And so we ran a life test. We ran this unit with 600 pounds on it, 24 hours a day for 6 months. And at the end of 6 months running without any relubrication, there was still plenty of lubricant. We took them apart, we looked in the bearing, and we also looked at the ball screw, and there was plenty of lubricant left to continue running. So in many applications with a ball cage, you might be able to get away with considering them lubed for life. At the very minimum, you'll have a greatly extended lubrication interval. The cost for these, not much, maybe like 5%. It's well worth it. So specify the cage ball whenever you can. Now let's talk about the process of selection. Key factors to look at. Of course, the size. The bearing has to fit in your available space. The load capacity. What load capacity do you need in order to have a resultant life that meets your requirements? That might be 5 or 7 years in many medical applications. Of course, the life is based on the load capacity. Remember that the calculation is the dynamic load capacity divided by the load to the third power. So as you increase your load capacity of the bearing, you're greatly increasing the life of the fatigue life of the bearing. So you can kind of do a quick calculation when you're selecting a bearing. Do a quick calculation of what you think the resultant loads on the bearing will be, and see if that's going to meet your life requirements. Accuracy, what is your error budget? The way we look at it is how accurately do you need to be able to position to do the function that you're doing? And that's going to vary whether you're doing a scanning application, whether you're just doing point to point, but you have to take into account all of the accuracies of the system. They're all additive. So you're going to have a running parallelism of the bearing. You're going to have the mounting surface inaccuracies, not flat. You're going to have, of course, from your motion control system, you're going to have errors from whatever's driving the load. So all of these things have to add up to and still be within your accuracy requirements for your positioning. Stiffness, of course, we're especially looking at stiffness if we have overhung loads. We don't want the load having too much deflection. We're trying to hold the motion flat and parallel to your mounting base. Mounting tolerances, you should have a good understanding of what your machine shop is capable of doing. and then review the mounting tolerances requirements for the bearing you're thinking of selecting. Of course, preload, very, very important. After the selection of the bearing itself, the preload is probably the other most important thing that you have to get right. And then looking at duty cycle, cost, and any specialty requirements like vacuum, clean room, high temperature, corrosion resistance, and these types of things. A couple of other notes. Stiffness on the bearing, as I mentioned, especially important when you're looking at using a single bearing and an overhung load. Generally, we'll want to use a single wide bearing if we can, because then we don't have to worry about aligning two parallel rails. So if you can get away with using a single wide bearing, that's a good choice. Running accuracy and repeatability, again, mounting surface accuracy, the total accuracy is going to be made up of your running parallelism of the rail, how straight the rail is mounted, and the mounting surface accuracies. What is your speed? Cage balls are great for high speed. You can go up to 5 meters per second or higher in some cases with cage ball. And then what is the form factor? Is it going to fit into your application? So you're looking at your general layout. What's going to work for your positioning requirements? A cantilever, a stacked XY stage, a gantry. You've got to determine that based on doing your initial layout. Here I'm showing a cantilevered. Now on the left-hand side here, I'm showing a cantilevered stage mounted XY. On the right, we've got a similar setup where you don't have stages, but you just have individual rails mounted to machine parts. And on the right side there, those are wall mounted. Now, as I mentioned, you don't want to use 2-row bearings on wall mount applications. This is a wide 4-row bearing. So they chose this correctly. Look at the number of axes. The orientation, is it going to be horizontally mounted, vertically mounted, wall mounted? And of course, then once you have your basic layout, we have to start looking at forces. What are the resultant forces on the bearings? So we want to start looking at the loads. You're going to have static loads just from your mass, the mass of the, if you have stack stages, of course, the lower stage is going to be carrying the upper stage. So you've got that static mass plus whatever your fixturing and your load is. So you've got that mass times the distance, or however distance they are from the rails. And you also have your dynamic loads due to acceleration. I want to take this second to point out a very useful tool. If you go to the website tech.thk.com, they have a really good service life calculator for linear guides, and you can choose pretty much any of their ball and roller type guides, 2 and 4 row, and it allows you to input your orientation and how the rails are going to be mounted. Is it going to be a single rail, double rail, single bearing, double bearings, and how far apart are they? How far apart are the blocks? How far apart are the rails? And the location of the mass. I've kind of given a picture of what it looks like where you're inputting that data on the website. It allows you to input your load information, the bearings that you're thinking of selecting, and also your dynamic information, the acceleration and duty cycle, and then it calculates back for you the loads on the bearings and the expected life. So this is a great tool. I will always use this tool when I'm doing an initial selection of the bearings because it's really quick, and I found it to be quite accurate. Of course, in more complex designs, we will also keep a spreadsheet table that explains all the forces and loads on the bearings and the resulting life calculation. We'll generally set that up so that we can change the variables, the distance between the rails, distance between the blocks, the actual load capacity of each bearing if we want to run our calculations with different bearings that have different load capacities. And once we get that set up, it's really convenient because we can just change the input of the load capacity into our spreadsheet, and it'll drops out the expected life. So just to review, static loads, you might have straight radial or reverse radial loads on the linear guide, or you might also have moment loads. Just some diagrams on the right. On the upper one, we're showing a offset load that will result in a rolling moment on the bearing. And on the lower diagram, in a vertical orientation, that offset load results in a yaw moment on the bearing. Of course, your similar calculations for dynamic loads, the load is, unless the load is perfectly centered and right on top of the bearing, you're always going to have some offset. And those offsets will result in moments as you accelerate. In this case, the load is offset both to the side and up from the carriage of the bearing. And that results in a yawing and a rolling moment due to acceleration. So this is an example of the calculations you can put in your spreadsheet, or that THK is doing for you behind the scenes as you do your calculations for fatigue life of the bearing. Other considerations, of course, humidity and moisture. Just a note on the smaller 2-row bearings that are really suitable for a lot of tabletop instrument type applications. Those are generally all stainless steel, so you don't usually have to specify that you want stainless, and that stainless is usually a Japanese version of a 440 stainless, by the way, 400 series stainless. So it's good, but not fantastic, but in moisture, humid applications. The temperature range, not a lot of medical applications that have high temperatures, but most of these bearings are available with metal end caps, and that would allow you to go over 100 degrees C if you have a wide temperature range. And then contamination. Do you have fluid? Do you have dust, chips, and what have you, where you have to look at what the enclosures, what kind of seals you want to specify for your bearing. And then finally, is it going to be in a clean room? Is this going to be moving in a clean room? Are you concerned about dusting? There are clean room, or what we call low dusting greases available that we can supply the bearing with that assembled into the bearing. And then we also have vacuum greases, which are low outgassing. We'll put these low outgassing bearings into very high vacuum, where a lot of times this will be a semiconductor application or similar, whereby whatever you have in the vacuum, what you're processing in the vacuum, you can't have any contamination from the grease of the bearing falling onto your part. So we have specialty cleaning that we specify, and special greases like a Krytox or similar low outgassing grease that we would apply. So let's look at some case studies of applications that we have worked on. So this picture is a picture of a motion system for a blood analyzer, a tabletop instrument. And basically they're doing cytometry. So they're mixing up cells into a fluid, and those would be put into a well tray. You have many samples in the well tray, and you're moving the sample tray under the pipette, which will come down and suck up the fluid, and then they do their analysis that they do to see, many cases, if you have cancer or other things in your blood. So the requirements for this motion system were that the sample tray position the cell under the pipetter within a certain tolerance. And so you might think you have something like a 2 millimeter hole in that well tray, and you have a a 1 millimeter pipetter coming down, and that gives you about a 0.5 millimeter on each side. So you want to be well within that as far as your accuracy. And remember, we're talking about the cumulative accuracy of your lead screw, of the X and Y motion system, both being straight, perpendicular to each other, and the carriage that's hanging off of the third rail, that carriage supporting your well tray is really flat. Because if that well tray is tilted, that'll take part of your error budget. So important in this application that the sample be held very accurately, that the motion be accurate, and that there be very little clearance in the bearings. So here, duty cycle was high, loads were light, but the positioning requirements were actually, we want them to be precision motion, and we wanted to have little or no clearance in the bearings. So we specify a preload. Key considerations here, because we're mounting this with an overhung load, we need to have roll stiffness, running parallelism and orthogonality of the sample tray, flatness of the sample tray, long life, low profile because we don't have much room here, and low cost. So we definitely want to avoid plain bearings. We can't have any clearance. So we're using recirculating guides, and what we chose was the wide series guide that can take a overhung load with a single rail. We chose those guides in, they came in stainless steel, and we specified a light preload. So we're basically using the same guide in all 3 axes. This simplified the assembly. Instead of trying to mount and align 2 rails on each axis, we only have to worry about aligning 1 single guide in the X to 1 single guide in the Y. We only really have to worry about making them perpendicular. So assembly time was reduced, and these worked very well in this application. Out of curiosity, I have some, I was looking at, we actually build this particular assembly, and I was looking at, we check the motion profile of each stage as we build it, and I just picked a random sample and was looking at it this morning. The max height difference over the x-axis of travel was 10 microns over the full travel. In this case, it's like 200 millimeters. Over the Y, it was also 10 microns, and the height difference, the max height difference of the tray was 10 microns. So that's exceptionally good. You might not always get quite that good, but I mean, you can see that you can hold some pretty tight tolerances with even with the standard 2-row single bearing. Next application we'll talk about is a microtome. So for those of you who don't know what a microtome is, this is used for slicing tissue. The doctor might take a biopsy if he thinks you have cancer. They would take that biological sample and they would put it in a cup with wax, generally, with fluid wax, and then allow it to harden. They put that sample mounted to a fixture on the end of that brass shaft shown in the picture here. And there would be a blade mounted to the base at the bottom. And as that shaft moves up and down, it brings the sample by the blade, and as it goes up and down, it indexes out as little as 1 micron and as much as 40 microns. And so as you start to cut, every time you go up and down, it can index out as little as 1 micron, but generally they're cutting more like in the 5 to 10 micron range. They want to get a full slice of the tissue to look at under the microscope. Now that tissue slice has to be very, very uniform. And what affects that is the rigidity with which the sample is held. So really the most important thing in this application was that we make the strongest, most rigid support for the sample that we could. So you can see we started by using a very, very rigid machined part supporting cross roller stroke bearings. That allows us to control the preload, and being that these are rollers, they have the higher stiffness. So that's what how we supported the load in the z-axis. In the extending or y-axis, because we're making such small movements, we're only moving between 1 and 40 microns with each slice. We actually can use a plain bearing here. We don't need rolling elements supporting the load. The friction is minimal because of this such small movement. So what we did is we put a very tightly controlled diameter brass shaft into a very tightly controlled bore. In this case, it's a aluminum housing with an anodized bore that's lapped very, very tightly to the diameter of the shaft. And so you still end up with virtually almost no clearance between the two and a very large surface area to support the load. And that results in the maximum stiffness. And so with that, we're able to cut samples that are very smooth and accurate. What we found is any clearance in the system will result in what they call Venetian blinds. Users of this equipment, they call it Venetian blinds. And what that is lines, vertical or horizontal lines across the sample, going through the sample, many, many lines that kind of look like a Venetian blind. And when that happens, the sample is just unusable. You can't look at it. You can't look at the cells under the microscope. So very important here to have maximum rigidity. So of course, because this piece of equipment is getting wiped down with alcohol and disinfectant, the guides had to be stainless steel. Of course, the shaft is corrosion resistant with being brass. So we specified the cross rollers for stiffness in stainless steel, and we designed our own brass round plane bearing for the y-axis. Let's look at this last application. This is a medical bed that we designed. And so it's 5-axis bed. So let's look at the x-axis. X-axis was actually the lateral movement, which was relatively short. We only need 10 centimeters of travel. The y-axis is the long axis, moving the patient. We go back here. This whole upper portion moves all the way out. You can imagine the patient laying on the carbon fiber bed, the part that's overhung off to the front of the bed. And the reason they do that is because you don't want any metal. If you're for several different types of medical applications, you don't want any metal in the treatment area. So the carbon fiber doesn't show up. It's very radiolucent if you're sending radiation through the patient, or if you have any type of magnetic field, the carbon fiber doesn't affect that. So you lay the patient on the carbon fiber bed and you extend them into the machine to do whatever treatment you're doing. So the y-axis is that long axis. Now the y-axis is supporting all the other loads. So you have to take into account the heavy moment load based on the overhung cantilevered load of the patient, and all the other axes that are mounted on top of that. So what we chose was, on the y-axis, we chose the 4-row recirculating ball type bearing of substantial size. I believe in this case, we chose size 30, which is a 30 millimeter wide square rail with 4 bearings. And the resulting load capacity there was high. And we, of course, chose a preload because we can't afford to have any clearance. And that was able to support the load with maximum rigidity. You might say, because we've got a very heavy overhung moment load, why didn't we use recirculating roller type bearings? Well, the reason we didn't was because space was not so much of a constraint. We could afford to have a little bit larger ball type recirculating bearing in there we didn't need to downsize. And so the ball rail was less expensive and more available than the roller type. You might make a different choice. Space might be more of a premium in your application, but in this case, we didn't need to. And then the Z-axis, same large 4-row, 45-degree contact angle, recirculating ball type bearing with multiple bearings supporting the load. So in conclusion, make sure you define your requirements. Look at all of the different things we discussed in the beginning that should be taken into consideration: preload, environmental concerns, your duty cycle, the form factor, again, looking at the load capacity, cost. And one other thing to keep in mind, customization. I didn't really talk about it, but many of these guides that we apply end up being customized in one way or another. Some easy customizations that are readily available from the factory are additional holes in the rail. You might specify a dowel pin for whatever reason, maybe for a stop or positioning for some reason or another. Those are all readily available. There are also more exotic modifications that the factory will do. Now, keep in mind, if you happen to be a very large robotics manufacturer and you're potentially going to buy hundreds, if not thousands, of this bearing a year, the factory may bend over backwards and design something very specific for your application. They may put extra holes in the carriage, or we've actually seen them put a special profile on the rail. We had rails that were in a robotic surgery application that were that actually were exposed, and that the doctor or nurse would put a drape over, and what they found was the sharp corner of the rail was cutting the medical drape. So they actually asked the factory to make a rounded cross section of the rail so that to eliminate that sharp corner. Now, you or me, and we're going to buy 10 of these, forget it, they're not going to do that. But if you have a high volume application, they might do it. So keep in mind, easy customizations and more exotic customizations may be available. Talk to your vendor to see what's available. And that concludes our presentation.
Wally, thank you for a really informative presentation. We are over our initial 45 minutes, but there are some questions that we have. So let's get to at least a few questions that might be on people's minds. First question I have is, what are the most common mistakes that are made in designing linear bearings for medical applications?
Yeah, definitely the most common mistake is not having proper mounting tolerances for your rails. And whether that's that you talk to your machine shop and said, well, what's the best you can do? And you put that down, and believe me, I've seen that many times. Or if the machine shop just isn't able to meet print and the parts come in out of tolerance, when you go to mount your rails and as you tighten everything up and align it and you mount the carriage to the bearings, and all of a sudden the friction goes through the roof. That's very common. Other things, installation errors, maybe you don't get the rails as parallel as they should be, or you maybe chose the wrong rail for the application. But yeah, mounting tolerances and installation errors are probably 1 and 2.
Which type of bearing typically require a preload?
So all of the bearings are able to be preloaded except the plain bearing that we talked about in the beginning. Only really the cross roller type bearing actually requires a preload. You at least want a light preload to make sure that all of the rollers are in contact, line contact, and rolling. With the recirculating type, they don't require a preload. You can run them with clearance, and that's actually pretty common to run them with clearance. And the reason somebody would do that is because because you're actually allowing a little bit more forgiveness for your mounting surface errors. And by the time you mount the bearing up with the rail and the carriage all mounted to a base and a top plate, generally you've used up all of that clearance, and you result in a preload anyways. So yeah, not all of them have to be preloaded. Only really the cross roller has to be preloaded. But all of them except the plain bearing are able to be preloaded.
Thank you, Wally. Well, let's get to one more. What are the most common causes for bearing cage failure?
Yeah, that's a good question. Cages are extremely durable. I've seen them, as I said, we ran it for 6 months under really heavy loads, didn't have any issue. In fact, I've never seen a cage just completely wear out just from running. I have seen cages damaged on installation, and you don't realize it. A lot of these bearings come separate from the rail, and your technician is required to install the bearing on the rail. It's really easy to grab that corner of the rail as you're pushing the bearing on. And if you tear that cage, you might not notice it at first, but you are going to have premature failure. So make sure that when you're installing the bearings on the rails that you use the fixtures that come with the bearings. Make sure that the bearings are really well lined up when you push them on, and that you don't force them. Just a light finger push to get the bearing on, and if you have any resistance, stop, reset, make sure you're lined up, and do it again.
Thank you, Wally. Thanks to all of you for joining us for this webinar. We will be emailing you our recently published 18-page white paper with the same name, How to Select the Ideal Linear Bearing for Your Medical Application. As well, we'll be sending you a link to be able to view this presentation on demand, or if you want, share it with other people. We'd appreciate your comments on the value of the webinar, and if there's other topics that you'd like to see us address. Wally and the entire Motion Solutions team looks forward to working with you on your projects. Thank you again for joining us. Have a good day.